Okay, we're going to look to show here how our improper integral converges for values of p that are greater than 1, but diverges for values of p that are less than or equal to 1. We need to show this because by the integral test, what we're trying to show is any series that looks like this, which is known as a p series, that will converge as well for values of p that are greater than 1, but it will diverge for values of p that are less than or equal to 1. And this is by the integral test. Okay? So this is really what we're going to use here. All right. So we start with the integral from 1 to infinity, 1 over x to the p power dx, which is defined to be the limit as x goes to, t goes to infinity as we integrate from 1 to t, 1 over x to the p dx. So we're going to focus on this particular integral here. From 1 to t, I write it as x to the minus p dx. Okay. All right, let's see how this goes. So what we know is this is going to be x to the negative p plus 1 over negative p plus 1, evaluated from 1 to t, which we write as x to the 1 minus p over 1 minus p from 1 to t now. So substituting our limits here, we get t 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Now let's double check here. Looks good. And just to remark here that this portion will be 1. And so we really have, I'm going to factor out this 1 minus p term. T to the 1 minus p, really minus 1 now. Okay? Okay. So this is the I of t integral that we typically define here. This is our I of t. Now, okay, we're going to now take the limit. However, let's notice what the limit's going to say. We're going to take the limit as t goes to infinity of 1 over 1 minus p, t to the 1 minus p minus 1. We're going to pull out the constant of 1 over 1 minus t. We'll look at the limit as t goes to infinity, t to the 1 minus p minus 1. So we're going to focus on a few things now here. We're going to look at cases now for p. So we're going to note something, by the way, that we've seen earlier. When p is 1, we had the harmonic series diverge. So when the case for p is 1, we already know we get divergence here. We don't have to use this formula that we just derived. This is just from what we looked at earlier today. Okay, so we're going to look at cases of P now. So the second part we want to talk about is what happens when P, or we should say 1 minus P, this power, is negative. Now this is what we're saying here. What happens when that's actually negative here, which means if we solve for P, P is really bigger than 1. And that's what we're looking at. So let's look at the limit here. Okay, so what this means is as T goes to infinity, we know that T to the 1 minus P will go to 0. So what we're saying here, let me copy this portion. We try to copy. Is that this portion over here goes to 0. So that the limit now is really going to be negative 1. And so we get 1 over really P minus 1. And what we're concluding here now is that when we integrate from 1 to infinity, x to the P, the x will be 1 over P minus 1, which is finite, only when P is bigger than 1. So we get convergence here to the value 1 over P minus 1. This number is a finite value. Okay, now the second case we're going to look at here, if we go back to this particular integral again, okay, we're looking at these cases here. Copy. Is we're going to consider the case where that power again of 1 minus P here is positive, which means P is smaller than 1. So we're going to look at that case and what happens to the limit here now for this. And so P smaller than 1. All right, so now again, as T goes to infinity, T to the 1 minus P, that's going to go to infinity. So this portion goes to infinity, which really means we have 1 over 1 minus P, infinity minus 1, which is really a value times infinity. This diverges here. So this answer is infinity. What that means is the integral now from 1 to infinity, 1 over x to the P dx is actually infinity, diverges for this value of P over here. P being less than 1. Okay. So in conclusion, we only have convergence when p is bigger than 1. This is the convergence here. This is what we want to know and use. And down here is where we have the divergence. But don't forget, we got to include the harmonic series as well, where p is actually less than or equal to 1. So what does that mean about our particular p series? Well, that means the p series defined to be 1 over n to the p from 1 to infinity converges only for p values being bigger than 1. And diverges for all the other values, p being less than or equal to 1. And that's what we wanted to set out to prove. The conditions where you have convergence of this p series. Convergence happens for p being greater than 1, and then divergence happens for p being less than or equal to 1. And that is what we set out to demonstrate.